Hi everyone, it's Mr. Bowman, and in this video we're going to go back to section 4.3 and we're going to focus on the 6 trig functions for angles outside of the first quadrant. So we're going to cover lots of things today, but it's all going to tie together. The first thing I'd like to talk about are 2 special right triangles, and one of them is the 45-45-90 right triangle. And I'm going to use radian measures for this. So let's say we have a radian measure of pi over 4, and the right angle there. If you recall from your days in geometry, the relationship between the legs is that the legs are congruent, and that would make the hypotenuse the leg times the square root of 2. And you can verify that with the Pythagorean theorem. What we're going to do today is we're going to switch things up, and we are going to make the hypotenuse a length of 1. So here's our 45-degree angles. Again, same as pi over 4. But instead of making the hypotenuse the leg times root 2, we're going to make the hypotenuse 1. And so if we have to multiply by root 2 to go from the leg to the hypotenuse, we have to divide by root 2 to go from the hypotenuse to the leg. So each leg would be 1 over root 2, which if we rationalize it is going to be root 2 over 2. All right. The next special right triangle that we want to deal with is the 30-60-90, and in the 30-60-90 I'm going to start with radian mode. So the 30-degree angle pi over 6, the 60-degree angle pi over 3, and the 90-degree angle. If you recall from your days in geometry here, the short leg would have a length of x, the long leg x root 3, and the hypotenuse 2x. So what we're going to do is we're going to again change the hypotenuse to 1, and instead of taking the short leg and doubling it to get the hypotenuse, we're going to take the hypotenuse and cut it in half to get the short leg. So 1/2. And then we're going to take the short leg and multiply it by root 3 to get the long leg. So 1/2 times root 3, or root 3 over 2. Why are we reviewing that? We're reviewing that because we are going to use those 2 reference triangles extensively when we're finding the trig ratios for the angles that we're interested in. So before we do that, I want to remind you all that the definitions of the trig ratios are given in this green table here, and you will notice that at times some of the angles are undefined. For example, if the x value is 0, the tangent is going to be y over x, and you can't divide by 0, so the tangent is undefined. Now, I know that many of you first learned trig from right triangle trig, and you are used to using SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And I'm fine with that when we get to angles outside of the first quadrant, as long as you draw a reference triangle. So, for example, if we were trying to find the sine of this angle over here, by definition, it is y over r, the y coordinate of a point on the terminal side of that angle divided by the distance from that point to the origin. You can't use SOHCAHTOA on this picture unless you draw a reference triangle. If you draw a reference triangle like this one right here, then you can use SOHCAHTOA as long as you pay attention to the sine of the plus minus sign when you're trying to find the sine, cosine, tangent, and the reciprocals. So a few things that I'm going to recommend here for finding trig ratios for angles outside quadrant 1. Number 1, draw a reference triangle. Number 2, go ahead and use SOHCAHTOA but pay attention to the sine plus or minus of the sine, the cosine, the tangent, and the reciprocal functions. And then lastly, there are times where you are going to be asked to find the sine, cosine, tangent, or the reciprocal functions for multiples of 90 or pi over 2. Those you have to watch out for. So watch out for trig ratios at multiples of pi over 2 or 90 degrees. Why? Because first of all, you can't have a reference triangle at multiples of 90, and second, some of the trig ratios are going to be undefined at multiples of pi over 2. So a moment ago, when we looked at these special right triangles and we made the hypotenuses 1, you may have wondered why that would be the case, why we would do that. Well, the reason that we do that is the following. This diagram you see here is called the unit circle, and it's called a unit circle because r is equal to 1. The radius is equal to 1. So, for example, if we were going to find the cosine of an angle, let's just pick a random angle here. Let's say pi over 6. We're going to make our reference triangle. Our angle here is pi over 6, or 30 degrees. R, the hypotenuse, is going to be 1. The cosine is defined as x over r, which in this case would be root 3 over 2 divided by 1, which is root 3 over 2. Essentially what we're saying is the cosine of theta is equal to x, because r is equal to 1 when r is equal to 1. Similarly, the sine of theta, which is equal to y over r, is going to be equal to y when r is equal to 1. What that does for us is it basically allows us to take a look at these coordinates of these points at the end of the hypotenuse, or at the end of the radius there, and start to recognize some patterns there and boil it down for these special angles to 3 cases: a 30, 60, 90 right triangle, a 45, 45, 90 right triangle, or what we call a quadrantial angle, which is a multiple of pi over 2 or 90. So essentially, what we want to do is we want to do a little practice finding trig ratios for angles outside of quadrant 1. So we're going to do exactly what I said we should do earlier. We're going to draw a picture. So 3 pi over 4. So if you're struggling drawing a picture of these because you're a little rusty on radian measure, I usually think of it the following way. If I want to find the cosine of 3 pi over 4, basically it's the cosine of 3 times pi over 4. And think of pi as being replaced with 180. So 180 divided by 4 is 45. 3 times 45 is 135 degrees. So we've got the cosine of 135 degrees. Remember, we're starting in standard position, the positive x-axis. We are rotating counterclockwise till we get to a 135-degree angle. So here's our 3 pi over 4 or 135-degree angle. And then we're going to draw a reference triangle here. So there's our other pi over 4, and we're going to make the hypotenuse 1. So that means the legs are going to be 1 over root 2, or root 2 over 2, 1 over root 2, root 2 over 2. And the cosine is x over r. So x, 1 over root 2 over 1. Basically, that's why we made the hypotenuse, or the radius, 1, is so that now the cosine is just x instead of x over r. So 1 over root 2 over 1, or root 2 over 2 over 1, is going to be root 2 over 2. But you have to pay attention to the sign. We're in the second quadrant here, so x is going to be negative. This next one here is one of those multiples of pi over 2 that I was talking about. So pi, the same as 180. So we rotate around here, pi radians, or 180 degrees. And we're going to put a point out here. Remember, we're making r equal to 1. The distance from the origin is equal to 1. So the coordinates of this point would be -1, 0. And the cotangent is x over y. The tangent is y over x. So the cotangent is x over y. And x over y in this case is going to be -1 over 0, which is undefined. Here we go again with the pi angle measure. So we rotate pi radians, or 180 degrees, radius of 1. So our point out here is going to have coordinates -1, 0. And the cosine is x over r. X is -1. R is always going to be positive over 1. So we have -1. And then finally, we'll do one more here, the cosecant of 4 pi over 3. Again, I would treat this, if I'm struggling with trying to figure out where that's located, I would treat this as pi over 3, or 180 divided by 3, which is 60, times 4. So really, we're finding the cosecant of 240 degrees. So that helps me a little bit because I start at the positive x-axis, rotate 180 degrees. I've got to add another 60 to that. So there's my 4 pi over 3 angle, which is 240 degrees. And I need to draw my reference triangle. So I've got a 60-degree reference angle here. That makes this 30. If the hypotenuse is 1, the short leg across from the 30-degree angle is half of that, and the long leg is 1/2 times root 3, or root 3 over 2. Again, pay attention to the sign, the plus-minus sign. So the cosecant, the reciprocal of the sign is y over r, which is going to be root 3 over 2 over 1. So we're going to take the reciprocal of that, 2 over root 3 over 1, but there's a negative in front of it, and typically that would be rationalized, so -2 root 3 over 3. All right, so you're going to have to do a fair amount of these to get comfortable with them. There's no rush in doing these. Take your time, draw a picture, think it through, go back to the definitions for the sine, the cosine, the tangent, and the reciprocal functions if you have to, and watch out for those quadrantial angles, those multiples of pi over 2. So there's all kinds of ways that you can go about this, and I am not encouraging you to memorize the unit circle, but I do want to point out some patterns for you that I think are relevant. So if we take a look at this diagram here that's color-coded, all the angles that have a red terminal side, which there are 4 of, are multiples of 30 degrees or pi over 6. And what you'll notice here is that the x, y coordinates of points on the terminal side, when the radius is equal to 1, are going to always have this pattern. The x coordinates are either plus or minus root 3 over 2, and the y coordinates are always plus or minus 1/2. So the sine or the cosine of any of those, the cosine is going to correspond to the x coordinate, the sine correspond to the y coordinate when the radius is 1. If we have 45-degree angles or multiples of pi over 4, you'll notice them up there with the green terminal sides, and you'll notice they all have a relationship as well that's similar. All the x coordinates are plus or minus root 2. All the y coordinates are plus or minus root 2 over 2. And all the y coordinates are plus or minus root 2 over 2. And these all come from those special right triangles where we made the hypotenuse 1. Multiples of 60 or pi over 3, you will notice in our diagram, are color-coded in yellow, and the x coordinates for all of those are either plus or minus 1/2, and the y coordinates are either plus or minus root 3 over 2. And then finally, the quadrantial angles, the multiples of 90 or pi over 2, the x, y coordinates are either plus or minus 1, 0, or 0 plus or minus 1. And again, that's the reason that we use the unit circle, because then it makes the sine and the cosine of the angles that we're interested in equal to the x and the y coordinates. So at this point, we are finished with this video. What I would like you to do is pause using this diagram here in front of you, go through these examples here and try and find the exact values of these trig ratios without using a calculator, and try and do them without using the diagram above unless you have to. When you're finished, unpause the video and scroll down and take a look at the answer. Okay, so here are the answers that you should have gotten, along with some pictures to go along with them. If you have any questions on any of these, please make sure to ask your teachers.